Before the break, a long time ago, almost 2 weeks ago now, before the break, we introduced this concept, this discovery that was made almost 200 years ago by a guy named Hans Christian Ørsted. And that discovery seems like a pretty simple one, but it is arguably one of the most important discoveries in the history of technology. It is the basis behind just about every bit of modern technology that exists today. That discovery is this: electricity produces magnetism. Electricity produces magnetism. Simple as that. Electricity produces magnetism. Well, let's provide a little bit more detail on it. It's not quite as simple as that. What do we mean by electricity produces magnetism? Well, if you have a single charge, positive or negative, and it's sitting there, it's not doing anything, it's not moving, it's not accelerating, it's not doing anything, it's just sitting there. That moving charge will produce an electric field. It will produce a gravitational field because presumably it has mass. It will not produce a magnetic field. If it's just sitting there, it won't make magnetism. In order for electricity to produce magnetism, that moving charge, whether it be a positive or a negative charge, has to be moving. So if it's at rest, it produces an electric field. It will also produce a gravitational field. If it's moving, it will still produce an electric field. It will still produce a gravitational field because it has mass. But if it's moving, it will also produce a magnetic field. So the basic discovery is electricity produces magnetism, but if we provide a little bit more detail here, that electricity has to consist of moving charges. And that magnetism that's produced is not some kind of magnetic force or anything like that. It's a magnetic field. So moving charges produce magnetic field. Now, we learned on Wednesday before the break what that magnetic field will look like. Does anybody remember the shape of the magnetic field that surrounds a moving charge? If we have a bar magnet, it's going to look something like this, right? Okay, we looked at this for several days before the break. A bar magnet going to have a magnetic field that points from north to south outside of the magnet. If we look at inside the magnet, it would actually be from south to north. Okay, that's the magnetic field surrounding a bar magnet. What does the magnetic field surrounding a moving charge look like? Maybe we've got a moving charge, moving electron represented by the X. What's that X mean, by the way? Direction, right? Into, out. Which one is it? The X is into the page, yeah. So let's say we have electrons moving into the page. The magnetic field surrounding that moving electron would be circular. Circular magnetic field. That's the shape of it. Now, that's one field line. Another field line would look like this. Another one would look like this. Notice they get further away from each other the further they get away from the moving charge. That should make sense, right? The further you get away from the producer, the weaker the field is going to be. The further the field lines are going to be away from each other. Now, how is it exactly that we determine the direction of the magnetic field? Here's the shape. Okay? Moving charge generates magnetic field. It's a circular magnetic field, concentric circles that get further apart from each other. What's the direction of the magnetic field in that circle? Yep. How do you know it's clockwise? Okay, so did you just remember that? When a charge is going into the page, it makes a clockwise field? Or do you have a way of figuring that out? Something? Oh, the thumb. Oh, they said something. Okay, the thumb. So what are you doing with your thumb? Because you could hitchhike with your thumb. Although in today's day and age, I wouldn't recommend that. Crazy people out there. What else can you do with your thumb? Okay, left hand, because it's a negative particle, so left hand. If that was a positive particle, like a proton or an alpha particle, we'd use our right thumb, right? Okay, so left thumb, negative particle. Good, keep going. Okay, so stick your thumb in the direction, you said, like out of the page, like on the page like that? I think you said that, right? It would be into the page, right? Now, for me, into the page is towards the front of the room because my page is vertical, right? For you, into the page would be toward the floor because your page is horizontal. That's okay. Okay, we're not going to get bothered by that. The fact that your page is oriented differently than my page. Okay. Bottom line is your thumb goes into the page. Now, you're going to bend your fingers a little bit or a lot. Doesn't matter. A little bit or a lot. Looking at which way your fingertips point. Okay. Right now, I got my thumb into the page. Right now, I got my fingers bent a little bit. They're pointing counterclockwise. If I bend them a lot, my fingers might point still counterclockwise. Or a whole lot, my fingers still point counterclockwise. So as long as you get your thumb pointing into the page, bend your fingers a little bit or a lot, you're going to point counterclockwise. Or as those of us who grew up in the UK would say, they would point anti-clockwise, right, as opposed to counterclockwise. Same deal, right? Let's do another example of that, actually. Let's say we got this time, let's say we got an alpha particle, which is a positive particle that's once again going into the page. Same shape, and always circular magnetic fields, further away from each other, meaning field gets weaker, further you get away from the producer. The direction here going to be right hand, right, Cole? Right hand this time because it's a positive particle. Might not be a bad idea, in fact, when you see a question involving a hand rule, especially when it's involving a positive particle, to draw attention to that. Even make a little note, right hand, because that's a real common mistake. We get so used to using our left hand for one of the hand rules because we're used to using negative particles. We see that positive particle, we just automatically use the left hand. So it might not be a bad idea to draw attention to it. Right hand rule here, thumb goes into the page. Everybody try this. Okay, everybody try this. I don't care whether you use my page, the vertical one, or your page, the horizontal. Put your thumb into the page. And then bend your fingers a little bit or a lot. It doesn't matter. Okay, in any case, my fingers are going to point clockwise here. So the magnetic field would look this way. Or, as somebody in the last class pointed out, anti-counterclockwise, which I guess would be clockwise. Anti-counterclockwise. Let's just go with clockwise. Okay? Magnetic field would point clockwise here. One more example. This one's going to be a little bit more challenging. This time we got a current going towards the left side of the page. We'll make it an electron current. Right? The electron's flowing through the wire. When you got a wire, it's almost always going to be electron current. Now, having said that, there is a term that I've seen a handful of times, maybe 5 times over the last 20 years on a diploma exam, a term called conventional current. It's rare that we see it, but it's not out of the question. Electron current is the flow of negative charge, left hand. Conventional current is the flow of positive charge, right hand. Got it? Probably won't have to use that. Right hand, you will have to use that. But the term conventional current, you probably won't see. But you could. If you do, remember conventional current, right hand. Electron current, left hand, conventional current, right hand. Okay, so we're saying this is electron current that we got in this question. We're going to use our left hand. It's pointing to the left thumb towards the left side. Now, we want to find the direction of the magnetic field above the wire, below the wire, in front of the wire, behind the wire. Some of you are good artists. Some of you are much better artists than me. I'm terrible. I can try to draw this. Kind of looks something like that. Magnetic field is going to go around it, right? If this is my wire, it's going to go around like this or like this. Works better for me if I just express it in words, though, as opposed to drawing it out. You can draw it out, that's great. Okay, if you can't, express it in words like I will. Here's the wire. And remember, for me, my page is vertical, right? Because that's my board. That's my whiteboard, vertical. Everything I say now for direction will be relative to you, by the way. So if I say in front of the wire, not in front for me, but in front for you. Okay, you're looking at this side of the wire is the front. Okay, it's not for me, but I know this already, so it's you that we're using as a frame of reference here. If I say to the right, I mean to your right, not to my right. Okay. Let's stick your thumb to the left side of the room, towards the left of the page. Now, I want my fingertips, not your fingers, your fingertips. Like, look at your fingernails. Paint them. Paint your fingernails pink or yellow or orange. Remind yourself that you're looking at your fingernails, your fingertips, not any other part of your fingers here. Let's put my fingertips right above the wire, right above them. Not out here, because that's not above the wire. My fingers are above the wire. My ring is above the wire right now. But that's not what I want above the wire. I want my fingertips above the wire, my fingernails. When my fingernails are above the wire, which way are they pointing? Remember, this is my page, like this, vertical. Which way are my fingertips pointing right now, James? Towards the back wall, yeah. But let's say it relative to my page. Because for you guys, your page is different, right? For you guys, it's not going to be towards the back wall. But relative to the page, it'll be the same answer. Pointing up the page? No, this is my page. Which way are my fingertips pointing? This is my page. Okay. You're looking at the front of the page. My fingertips are pointing out of the page, right? Yeah. That makes sense? It gets a little bit confusing, guys. It does. That's okay. That makes sense, guys? Fingertips are pointing out of the page. Okay, I need to, I don't know, dress up like a page or something so you can see that my fingers are going away from me, out of the page. Sorry?
Yeah, you were saying the page is in front of your hand.
Well, it doesn't matter. The page is vertical. No, the page doesn't matter whether the page is here or page is here. No, it doesn't. No. Oh, I see what you mean. Yeah, no, I see. Okay, fair enough. No, fair enough. I see what you mean. Okay, the wire that I have right here is on the page. Got it? The wire that I've got is on the page. So the page goes here. Not here, not here, not here. Page goes here. Got it? Got it? So which way are my fingers pointing right now? Out of the page. Right. Good. Okay, I understand the confusion. Yeah, that was my fault. Right now, my fingertips are below the wire. And which way are they pointing right now? If this is the page, they're pointing into that page, right? Okay, right now, my fingers are in front of the wire right now. Which way are they pointing? Down the page. Now, this is the one that becomes a little bit more challenging. Start manipulating your fingers around like this, try to get them behind the wire like this, and your body has to do strange things to orient it like that. This is, I've told you guys before, one of the worst parts about this job is test day. When everybody's writing a test and I'm just bored out of my skull because I'm just watching you guys write tests. Except for this test. Magnetism is actually kind of entertaining for me. You've learned one hand rule right now, the Wiregrass Rule. You'll learn another one today called the Coil Rule, and then you'll learn another one tomorrow called the hand rule for deflection. You're going to be doing strange, like Cirque du Soleil almost like things during the test of moving your hands around and your body around to try to see which way your fingers point and your thumb points. And sometimes it gets entertaining, actually, watching you guys contort your bodies the way you have to contort them to see which way your fingers point. But the funny thing is, like right now, I want my fingers to go behind the wire, and I have to contort my body, or it's what a lot of people do during tests. Or what you could do is just this. If you're having a hard time doing this, just turn your body a little bit. Makes it a lot easier, right? Right now, my fingers are behind the wire. There's the page. Which way are my fingers pointing relative to that page? Relative to that page, it's right there, Kirsten. Right there. Fingers are pointing toward the top of the page. Don't say up. Okay, don't say up. Because for you guys, hey, if we use your page, it's pointing toward the front of the room, right? Since my page is oriented different than your page, okay, our answers would be different if we expressed it relative to the room. Let's express our answer relative to the page. Okay, for me, it's up the page. For you, it's up the page. Okay, cool question? Good? All right, you good with that? Yeah. Yeah. Worksheet number 10 we assigned on Wednesday, what was it? The 3rd, 2nd, 1st, Wednesday, April 1st. It wasn't an April Fool's joke. It was due, but it's been a long, long time. You've probably got it done because you probably worked on it, finished it by the end of class. If not, don't panic about it. We're going to take a look at it now, though. So please take out worksheet number 10 out now if you don't have it out already. There's 6 questions on this page. We're going to go through all 6 of them. I'm not even going to give you the answers right now. We'll just go through the 6 questions and whether you think you got them or not. First couple start off pretty straightforward. Draw the magnetic field surrounding an electron current. I'm going to circle this electron current because I want to remind myself that negative particles, left-hand rule. It's going into the page, the X, right? So it's going to be left thumb into the page. Now for you guys, into the page is down toward the floor. For me, into the page is toward the front of the room, right? Doesn't matter. Magnetic field is circular. I could draw more field lines around that as well because there's an infinite number of them, but one is good for this purpose. Thumb in the direction of the particle. Fingers get quenched. Bent a little bit, a lot. It doesn't really matter. Okay. In the end, they're going to point counterclockwise, or as Josh would say, anti-clockwise. Here we got electron current as well, and in question number 2, also left-hand rule. This time it's coming out of the page. So here's our magnetic field shape. It's circular. Again, more field lines, but we'll just draw one for this question. Thumb out of the page. For you guys, it's right toward the ceiling. For me, it's toward the back wall. Fingers point clockwise. Good? First 2 questions good? Thumbs up? All right. 3, a little bit tougher, number 3. Okay, but we just did an example kind of like this. Once again, electron current. Electron current. We want to find the field above, below, in front, behind. Here's my wire. It's electron current, so it's going to be left hand. The current is pointing towards the right side of the page. Here's my page, vertical. Right here, right, James? Right on the wire there. Where are my fingers right now? Javi, where are my fingers right now relative to the wire? Don't tell me which way they're pointing. Where are they? Above, below, in front, behind? Above. Okay, good. They're above. Mason, which way are my fingers pointing right now? Yes, into the page. Good. So we're going to say above the wire. It's into the page. Now, you've got a couple options at this point. You can put your fingers in the rest of the positions. Above the wire, it's into the page. Behind the wire, it's down. Below the wire, it's out of the page. In front of the wire, it's up toward the top of the page. And you can put your fingers in all 4 of those positions. Or once you figured out what Mason's figured out there, above the wire, it's into the page. You can kind of just trace it around like this. Into the page, down the page, out of the page, toward the top of the page, all right? So do it once and then trace it around, or do it all 4 positions, doesn't really matter. Similarly with number 4, this time we got an alpha particle though. Big deal here, alpha particle. It's positive, so it's going to be our right hand for the first time. Here's the alpha particle moving up the page. For you guys, it's toward the front of the room. For me, it's toward the ceiling. Okay, alpha particle up the page. Right hand. Thumb toward the top of the page. Fingers, right now my fingers are to the right side of the alpha particle, and they're pointing, Ryan, which way are the fingers pointing right now? Yeah, toward the page, into the page. Okay. Behind the wire, it's to the left. To the left of the wire, it's to the out of the page. And in front of the wire, it's towards the right. You can, again, so like we did last time, Mason, once we figure out the first one, into the page, we can kind of just trace it around with our finger if we want and say, well, towards the left, out of the page, towards the right. And finally, 5 and 6 here. 5 and 6, a little bit different, kind of like algebra. Like in physics 20, I would give you a problem, or Mr. Coder would give you a problem. Here's the speed of a car, 25 kilometers per hour, travels for 10 minutes. What's the displacement? And you'd rearrange the equation v equals d over t, the equation that was provided to you, d over t, and you'd solve for d. D is equal to v times t. So you just rearrange it. Here we're kind of rearranging a hand rule. Usually we say thumb is the direction of the particle, fingers are what we're trying to find, which way my fingers point. This time it's, here's which way my fingers point, which way is my thumb pointing. I'm trying to find which way the thumb is pointing. So question number 5, electron, left hand. Instead of saying thumb points a certain way, we're going to say fingers go clockwise. Which way does my thumb point? Oh, wait, out of the page. So we're going to say out of the page there. The bottom one, alpha particle, right hand. Don't know which way my thumb points, right? We know which way our fingers points, going to be clockwise. Which way does my thumb have to point to get clockwise fingers? Into the page. Good. How many people got all 6 of those right? Okay. How many people feel like they could get all 6 of them right now? Less people than got them right before. That's interesting. We'll have ourselves a little quiz on that in the next day or two, either tomorrow or Wednesday. Good? All right. I want to show you one more thing here. One more rule here today. We're going to call it the Coil Rule or the Solenoid Rule. Your textbook calls this the Wiregrass Rule, but I don't like that name for it at all because in the end, that's what we call the last rule, is the Wiregrass Rule. And this rule is, although it's closely related to the last rule, it works opposite to the last rule. So we're not going to call it what your textbook calls it, the Wiregrass Rule. We're going to call this one the Coil Rule. Sometimes you see it called the Solenoid Rule. A solenoid is just a coil of wire. So we needed magnetism in grade 3 or grade 4. I don't know where it was, grade 3, grade 4, grade 5. One of the things that perhaps you did is took a nail, wrapped a wire around it, and attached that wire to a magnet. How many people did that in elementary school? Made an electromagnet in elementary school? Yes? Okay, a little less than half of you. That's a coil of wire. That's a solenoid. Becomes an electromagnet. We're going to learn how in the next few minutes to determine what the polarity of that electromagnet is, right? You wrap that wire around a nail, attached to a battery, pick up some thumbtacks. The nail has become a magnet, an electromagnet. Which end is north, which end is south? Yeah, that's what we're going to see here today. Here's my nail, or whatever core I put inside it, whatever piece of steel or iron or ferromagnetic material that I put inside it. Now I'm going to wrap some wire around that. There's my coil or my solenoid. You don't actually need, by the way, you don't technically need to have this piece of steel inside it, but it magnifies the effect. It makes it a stronger electromagnet if you have a piece of steel inside it. Kind of holds on to the magnetic field better. We're going to attach a battery to it, and that battery has a negative side and a positive side. And that's going to cause the electric current in that wire to move around clockwise. Now, this is independent of a magnetic effect right now. The current goes clockwise, not because of a magnetic field, simply because that's the way we attach the battery. You can see it's going clockwise. It's going to go up in front of this coil, down in the back, up in the front, down in the back, up in the front, down in the back, and so on. Goes around clockwise here. This coil or this solenoid becomes a magnet with a north pole and a south end, which end is which. Here's what I want you to do. I want everybody to take a piece of paper. Okay, it can be scrap paper from up at the front here. I've got a stack of it if you want, or just a piece of paper from your notes, doesn't matter. Take a piece of paper and roll it up. Make it into a solenoid here. This is your coil of wire. This is your solenoid right here. Everybody's got to do this. Everybody should have their little coil of wire, their piece of paper that's rolled up in front of them right now. You can see in the coil that I have drawn on the board that the current is pointing up in the front. Now remember in the last rule that we used, the Wiregrass Rule, for the Wiregrass Rule, which is not what we're using here. Remember that my thumb pointed in the direction of the moving charge or the electric current. My fingers, my wrapped up fingers or my clenched fingers or my bent fingers pointed in the direction of the magnetic field. This is the coil rule. This is different. For the coil rule, my fingers will point in the direction of the moving charge. In other words, the electric current. And my thumb will point in the direction of the magnetic field. So it's opposite. So if you look at this picture, you can see that the current in front is pointing up toward the top of the page. I want you right now, okay, this is my page, vertical right here. Okay, this coil of wire, this solenoid is on the plane of my page. Right now, I want you to, don't worry about bending your hand or anything of the sort right now. Just take your left hand, stick your fingernails, touch the front of the coil with your fingernails pointing up. That's it. Okay, don't worry about bending them. Just touch your left hand, your left fingernails on the coil in front. Okay, this is in front for you. Okay, don't worry about what I see. Okay, what you see. Okay, your left fingers pointing upwards in front. Okay. Yep. Yep. There you go. Okay, your left fingers pointing up. Everybody got that? Everybody do it. Some of you have a solenoid that's unrolling right now. Stick a piece of tape on it if it's unraveling on you. Fingers point up. Which way is my thumb pointing? Automatically, if I bend my hand just a little bit, which way does my thumb point? Towards the right? We're going to say the magnetic field here points toward the right. Now, that's the magnetic field inside the coil. Right? My fingers pointed up in the front, or you could have said, I suppose, down in the back. It would have been the same thing. Anyway, you look at it, my thumb is pointing towards the right. You don't want to have your fingers and your thumb parallel. You want to have your fingers and your thumb perpendicular like this, right? So, see what I'm doing there, guys? Thumb points to the right. Thumb's not pointing upwards like my fingers are. Thumb's pointing towards the right. So the magnetic field is toward the right, inside the coil. Now, outside the coil, the magnetic field would go around like this. That means which end is north and which end is south? Well, we know the magnetic field outside points from north to south, or inside it points from south to north. So the polarity would be like this. South on the left side, north on the right side. We'll do another example because I don't think you're quite there yet. That's okay. Another example. Here's our nail. Here's our wire that's wrapped around that nail, or a solenoid, or a coil of wire. This time we're going to make our battery oriented like this, with the positive side on the left side, negative side right here. That's going to give me a current that's going counterclockwise this time. Going to go up in the back, down in the front, up in the back, down in the front, counterclockwise. Take your fingernails, your left hand, right? Because we're dealing with electron current here. I'll tell you if it's conventional current, if it's positive charge. Okay, it's electron current. Assume it's electron current unless we say otherwise. Stick your left fingers, your left fingertips, not fingers, fingertips, fingernails, down in the front. Or you could put them up in the back, I suppose, but we get it drawn down to the front. Okay, careful. You have it down in the back there. So here's what I want you to do. Okay, take your hand, do this. Look at that, down in the front. There's the front, down in the front. Got it?
Okay.
Got it? Down in the front. Chris, does that make sense? Which way does my thumb point? Towards the left. So this time the magnetic field would point this way. This way towards the left. That means that this is going to be the north end, and this is going to be the south end. The magnetic field inside points from south to north. Now, we say it's north to south, but usually we're talking about outside. Inside goes from south to north. So north on the left side, south on the right side. Let's do another one. Here's my battery. Something similar to the first one now with a negative on the left side, positive on the right side. That means the current is going to go this way. Going to go up and in behind, down in the front, up in the back, down in the front, up in the back, down in the front, clockwise again. Hey, just like that first one, right? Current's going clockwise, and current's going clockwise here as well. All right. In the front, the current's going down. So in the front, we're going to stick our left fingernails, our left-hand fingernails, down. Just touch the front. And again, you're looking at the front here. Okay, not my front, your front. In fact, if that confuses you, let me do this. If you have trouble with this on your own page, label your coil. This is the front. If you have trouble with that, read it. It says front. It's important because it's in red. Stick your fingers down on the word front. Which way does my thumb point? Towards the left. That means the magnetic field goes this way toward the left. That means this is going to be north and this is going to be south. Does that make sense? Wait a second, though. I got a question for you. I don't understand something. In the first example, I had the current going clockwise, but I had a south-north magnet. In this one, I had the current going clockwise, but I had a north-south magnet. Can anybody explain to me why the polarity is reversed, but yet the current was going clockwise in both cases? Abby? Yeah. If you take a close look at the coil as it's the way it's wrapped around that piece of steel, you can see that it's kind of backwards, right? Right here, it's in front. Right here, it's behind. So that reverses the polarity. Lots of people, when they see a couple examples of this, they think, oh, I can memorize this. When it's going clockwise, here's the polarity. When it's going counterclockwise, here's the polarity. The problem with trying to memorize that is, well, it becomes all kinds of different possibilities, right? Okay, it's Current's going clockwise, counterclockwise. The wire's going in the front or it's going in the back, and it just ends up being too many possibilities. Don't try to memorize it. Understand how we determined this, and then you're better off. Does that make sense now? Okay, I'm going to give you one more example. This one's a little bit different. A little bit different here. Here's your nail. Here's your wire. Whoops. I can't even draw this now. That's what happens when you're away from school for that long. Here's your battery. Oh, didn't put a battery in there. I'm going to tell you that this is north, this is south. I want you to figure out which way the current goes. Which way does the current go? I'm going to give you about a minute to see if you can figure that out, then we'll take a look at it as a group here, okay? Which way does the current go? Is it going clockwise or counterclockwise? Does the battery look like this, or does the battery look like this? Okay, let's see what we got here. We know if we got a south pole and a north pole like this, south pole on the left side, north pole on the right side, we know that the magnetic field is going to go from, well, inside the coil it goes from south to north. Outside it would go around like this, right, from north to south, but inside from south to north. So I'm going to erase this because I don't think I really need that. As long as you remember that we're dealing with inside the coil right now, south to north. Now, usually we know which way to point our fingertips because we know which way the current points, and we're just seeing which way our thumb is going to point. This time it's the reverse. We know which way our thumb points. Our left thumb, because we're dealing with electron current, is going to point towards the right. So let's take your coil again. Okay, here's my coil. There's the front of it. We know that because it's labeled front. I'm not going to worry about which way my fingertips go right now. I'm just going to stick my thumb towards the right. Now, if I do that, okay, my fingers can go anywhere. I want my fingers to go in the front. Okay, my thumb is to the right. My fingers are in front of the wire. Which way are my fingers pointing right now? Towards the top of the page, or up the page, right? So that means that the current here is going to go up in the front, right? And it would go down in the back, up in the front, down in the back, up in the front, down in the back. If it's like this, it's clockwise. So those of you who voted clockwise there a few minutes ago were right. Now, if we want to draw the battery in here, the battery would be oriented like this, with a negative here and a positive here, because the electrons leave the negative end and then go back toward the positive end. Is that okay? You guys feel good with that? What is this you see up on the board now? It's a what? Did you whisper it? No, somebody did. Was it you? Somebody did. I heard somebody up here say, it's a speaker, yeah. It's a speaker. This is the first of a couple of applications we'll do using this whole discovery that was made almost 200 years ago by Oersted. Electricity produces magnetism. A speaker generates sound. Your iPhone, if you're listening to music, your iPhone doesn't generate sound. Your iPhone generates electricity. There's an electrical signal that goes through through the cord that's attached to the iPhone and then is attached to your earbuds or attached to the speaker, whatever the case may be. There's an electrical signal that goes through there that your iPhone generates. Now, your iPhone doesn't just generate random electrical signals. Those electrical signals are related to the sound that it wants to produce, but they're not sound. Okay, they're electrical signals. Here's the cord right here that's going to and from your earbuds or to and from your speaker. Now that cord, you can see, is attached to a coil, a solenoid, like this. Like this. So what happens when you get an electric current going through that wire, through that cord? It generates a magnetic field. In fact, it magnetizes that solenoid. It has a north pole and a south pole. Now, that electrical signal could go either way. It's going to change all the time, right? Because we want the sound to change all the time. The electrical signal will not be a constant current, not at all. But at a single given moment in time, there will be a magnetic field produced around that solenoid that is related to the current that was going through that solenoid at that moment in time. You got an electromagnet, which half a second later is going to look different. But for this moment in time, it's the way it is. Now, that electromagnet, you can see, is in really close proximity to a permanent magnet. Well, they're going to affect each other, right? You got a permanent magnet here, a pretty strong permanent magnet, by the way, that's really close in proximity to this electromagnet that changes all the time. That causes, the magnetic field that's caused by the electromagnet is going to cause the permanent magnet to move, to be attracted or repelled, depending upon the polarity of the electromagnet at that given moment in time. So the permanent magnet moves. Maybe it moves this way, maybe it moves this way, maybe it moves this way a lot, or that way a lot, or a little bit. Or maybe it moves quickly or slowly. It depends upon, again, the original electrical signal that comes from your iPhone. As that permanent magnet moves, it drags this cone with it. So if it moves forward, it pushes the cone out. If it moves backward, it pulls the cone back. As that cone moves back and forth, it changes the air pressure in front of the cone. Right? If you pull it back, then you reduce the air pressure. If you push it forward, then you increase the air pressure. What is sound? It's variations in pressure and air. So by this electrical signal, creating a magnetic field, pulling the permanent magnet back and forth, pulling the cone back and forth, you've just generated sound from an electrical signal that came from your iPhone or your CD player. Anybody have a CD player? Yes? No? Whatever it is, it's supposed to be generating the sound. Does that make sense? Here's another one. What is this? What do you see there? Let me flip the lights off so you can see that a little bit better on the board. What is it? Could be a fire alarm. Yeah, could be a fire alarm. Could be really any alarm, right? Could even be a doorbell, not the ding-dong doorbell. But I remember when I was a kid, a friend of mine used to have a doorbell. I used to think it was an odd doorbell. You push the button, and it would go ding, 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 as long as you held onto the button. When you let go of the button, it would stop ringing. So it wasn't one of the ding-dong doorbells, but it made noise, and they came to the door. Okay, it could be something like that, right? Now, you can see that this consists of a battery with a negative end and a positive end. A switch, which the switch could be literally the button on my friend's house, or it could be some switch that's controlled by heat or by smoke or by whatever. It's a fire alarm that you physically pull, okay, whatever. When the switch is open, nothing happens. You don't want your alarm to go off at random times. When the switch is closed, push the button or it's activated by fire or whatever. When the switch is closed, all of a sudden, electrons start flowing here. They flow through this make or break contact right here. So they flow through that make-break contact, which right now, by the way, is being made. The contact is made with this make-break contact. So it flows through there, up here, then down through here. Oh, look, goes through these solenoids like this, and then back up to where it started, and around and around and around and around and around. Make sense? As the current goes through these solenoids, they become electromagnets. They become magnetized. They develop a polarity. North, south, doesn't matter which end is which right now, okay? Doesn't matter. They develop a polarity. They become electromagnets. When they become electromagnets, they attract this thing, this piece of steel right here. They attract it. So this piece of steel, which right now is in location, we'll say it's location 1, is attracted to the electromagnets. So it's no longer going to be in location 1. It's now going to be over here in location 2. Piece of steel has been attracted to the electromagnets. The hammer goes along with it. What does the hammer do? Yep. Hits the bell. So what do you hear right now? Ding. That's it. So if you're paying really close attention, maybe you'll hear this fire alarm. Ding. You're going to think, was that the fire alarm I just heard, or was that just some ringing in my head? You don't want it to just go ding. You want it to go ding, 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 ding. So how do you get it to repeat? Well, the good news is the way it's set up, you don't have to do anything for it to repeat. What's happened here? As this green piece of steel connected to the hammer has hit the bell, the make-break contact has actually now been, let's go with yellow here, has actually been broken. There's no connection there. The current stops flowing. If the current stops flowing, then what happens to these electromagnets? They're no longer electromagnets. What happens to this hammer that's in position 2? It goes back to position 1. Just a minute ago, I said the make-break contact was made, then it was broken, now it's made again. What happens now? Repeats itself. So you're at a ding, the contact is broken, went back, was attracted again, the contact was made, you're at another ding, contact is broken, another one, ding, the cycle just keeps repeating itself 60 times a second or so. That makes sense? So now what you're in is ding, 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 as long as as long as the switch is closed. And you have the ability to run a current through there. Right? Good? Okay, here's what I'd like you to work on now. And you can have the rest of class to do this. There's some questions on page 592. Some check and reflect questions. This is chapter 12, by the way, if you haven't downloaded that chapter yet. Page 592, I want you to work on number 1 and 2, 5 to 8, and 10 to 16. You got about, about 13, 14 minutes in class here. You might finish these up. Class, if you do, that's great. If not, then let's finish those up for homework tonight, please.